Today on How It's Made. Aluminum pots and pans, artificial limbs, peanut butter, and the high-intensity light bulb. There are several different ways to manufacture aluminum pots and pans. Some factories have giant machines that simply stamp out or mold the cookware, while other factories use a technique called metal spinning. To make cookware that's safe for food use, the aluminum must be pure, no other metals mixed in. It all starts with a round aluminum sheet called a blank. They stamp the pot size and company name on what will be the bottom of the pot. They clamp it onto a lathe, centered against what's called the chuck, a metal mold shaped like the inside of the pot they're going to spin. The lathe spins at 2,000 revolutions per minute. Guided by computer software, the spinning tool, a round wheel made of a special plastic, pushes against the chuck, stretching and shaping the aluminum blank, much the way potters stretch and shape clay against their hand on a pottery wheel. Except that metal spinning works sideways, not up and down like pottery. The machine trims off excess aluminum as it rounds the edges. The factory has no use for these very sharp metal leftovers, but it doesn't throw them out. Aluminum is difficult to mine and therefore very expensive, so scrap aluminum is sent off to be recycled into other products. After the final trim to the finished size, another trimmer moves in to take the sharpness off the edge. It's taken 4 minutes to spin this 32-liter pot. Now it comes off the lathe. They punch out handle holes. Then rivet on aluminum handles. The pot is now finished. Items that aren't as large and heavy are spun on a hand lathe. This is where you need an experienced metal spinner. Because this trade isn't a mechanical science, you've got to have a feel for it. Besides cookware, many other aluminum products are spun on a lathe. This is a light reflector, that round aluminum fixture that covers light bulbs in factories, stores, and arenas. When working the hand lathe, the metal spinner uses what's called a scissor tool. It's the equivalent of the plastic wheel on the automated lathe. As the blank spins, he moves his tool further and further down to stretch the aluminum into the right shape. This is a sausage funnel. And this will be the inside tube of a cake pan. He makes the body of the cake pan on a different lathe, using a variety of tools to get a variety of effects. This beading tool creates an edge, for example. Almost all metals can be spun, though some are better suited for the technique than others. Aluminum and steel are very formable metals, so they provide the best results. Can a baking ingredient be the answer to global warming? Canadian researchers have found a way to transform harmful carbon dioxide into harmless sodium bicarbonate, baking soda. They mix CO2 with water, then force it through plastic balls treated with an enzyme from alfalfa. Today's artificial limbs are a far cry from the wooden leg of yesteryear. They look very realistic, and thanks to advances in prosthetic technology, artificial limbs function more and more like the real thing. They start by measuring the amputee's stump, what doctors call the residual limb. First, they measure the circumference at different points. Then the diameter at different points. They protect and lubricate the residual limb by coating it in petroleum jelly. Then they immerse it in algin, a gelatin-like substance that comes from algae. After about 5 minutes, they remove the residual limb. The algin has already begun to stiffen and maintain the limb's shape. A couple of hours later, it's stiff enough to be used as a negative mold. They pour in plaster of Paris, then insert a metal rod. The rod is what will later allow them to mount the dried plaster to work on it further. The plaster takes about an hour and a half to harden. They cut off the algin. Then, using sandpaper and files, they refine and smooth the surface. This plaster copy of the residual limb will now be used as a positive mold to cast the artificial limb. Often, they use a different technique to make the positive mold. They build a negative mold first using strips of plasterized cloth, much the same way they make a plaster cast when you break your leg. Then a scanner takes a detailed three-dimensional reading and programs it into a computer. A technician then makes any necessary modifications. They put a plaster block on a cutting machine. The computer guides the blade to carve out the positive mold. With either technique, once the positive mold is ready, they can make the artificial limb. The process they use is called lamination. First, they cover the mold in fabric socks. Some made of nylon, others of a material that contains fiberglass. They layer 6 to 10 socks in all, depending on how rigid they want the artificial limb to be. Then they coat the socks with a liquid resin made of either polyester or acrylic. Here they're using acrylic tinted to look like Caucasian skin. It's important to ensure the surface is evenly soaked. It's a meticulous process that takes about an hour. The acrylic solidifies in about an hour. Polyester takes about 12 hours. They then break the plaster mold inside, leaving a durable plastic shell called a socket. That will be the basis of the artificial limb. The socket connects to another plastic shell containing the mechanics. Or, like this artificial leg, the mechanism can be modular and covered in just a skin-colored foam. If the muscle at the site of the amputation still emits a good electrical signal when contracted, the patient can get a myoelectric prosthesis. It has an electrode that captures and amplifies a signal, triggering the artificial hand to open and close. As early as the 1400s, Africans made peanut stews. Peanut butter, as we know it today, was invented in 1890 by an American doctor. He used it as a protein substitute for people whose teeth were so bad they couldn't chew meat. The best peanuts for making peanut butter are runner peanuts because they're uniform in size. They roast more evenly than peanuts that vary in size. They arrive at the peanut butter factory already shelled. To make a 500-gram jar of peanut butter, it takes 565 grams of peanuts. That's about 1,100 peanuts. The first step is to roast them. The nuts travel through a hot air roaster heated to 204 degrees Celsius. The shaking motion moves them around so they roast evenly. More than 3,600 kilograms of peanuts go through this roaster per hour. When they come out, they've turned from white to light brown. Next, they go into another machine, which fast cools them at room temperature using suction fans that circulate air quickly. This rapid cooling process is critical. It halts the cooking and prevents the peanuts from losing too much oil. Next, the peanuts go through a machine called the blancher. It removes the outer skins by rubbing them between rubber belts. Then it splits the kernels and removes the heart of the peanut, which has a slightly bitter taste. But what's discarded doesn't go to waste. The skins go to farmers for pig feed, and the hearts go into bird feed. The peanuts land in a big stainless steel hopper. From there, they drop down into the grinder to be ground into a paste. At this point, the other ingredients go in: salt, sugar or another natural sweetener, and a small amount of hydrogenated vegetable oil, which acts as a stabilizer to keep the peanut oil from separating and floating to the top of the jar. Peanut butter contains no artificial coloring or artificial sweeteners. It has no preservatives either, yet doesn't need to be refrigerated. The peanut butter is finally ready. All that mixing has heated it up to 60 degrees Celsius. It goes through a cooling system to bring it down to 38 degrees. Now it can go into jars. Peanut butter is a healthy, protein-rich food with plenty of vitamins, minerals, and fiber. It has no cholesterol, but it does contain fat. The good news is that more than 80% of that fat is unsaturated. In other words, good fat that may actually help lower certain cholesterol levels in the blood. The bad news is that the rest of the fat content is trans fat or bad fat. It comes not from the peanuts themselves, but from the hydrogenated vegetable oil that's used as the stabilizer to keep the peanut oil from separating. If you want to avoid that, you can eat all-natural peanut butter, which doesn't contain a stabilizer. You'll just have to stir the peanut oil that collects at the top of the jar. Once the jars are filled with peanut butter, they go through the capping machine. The caps have an aluminum seal inside. As the caps pass through a heat machine, the seal drops down and adheres to the top of the jar, creating an airtight seal. A machine prints the production date and the expiration date. These unopened jars of peanut butter will stay fresh for 1 whole year. A household light bulb creates light through a metal filament. A high-intensity industrial light bulb uses not only a filament, but also coils, electrodes, and mercury vapor. It's more durable, but needs a cool-down period before relighting. In 1809, a British chemist invented electric light. Over the next few decades, other inventors produced electric lamps and bulbs, but the light didn't last very long. The big breakthrough came in 1879, when Thomas Edison invented a carbon filament that burned for 40 hours. Then, just a year later, he produced a bulb that burned for more than 1,200 hours. That finally made electric lighting feasible. They start by making the coil support through which they'll later thread the filament. They take a glass rod 11 millimeters long and heat it up enough to insert a pin just 28/100ths of a millimeter thick. The pin is made of tungsten, a hard metal that won't melt under high heat. The rod and pin go into a machine that heats the glass and presses it into a mushroom shape. Then they insert tungsten wires, just 0.0118 millimeters thick, 3 or 6 wires depending on the model of the light bulb. They cut the wires to the required length, which also depends on the model. Then they curl the ends into little circles. The coil support is finished. Next, they build the mount onto which several other parts will be assembled. They weld on the arc tube, a quartz tube containing a coil, electrodes, gas, and mercury. Next, they weld on the bimetal switch, which cuts the current to the coil in the arc tube. Then they weld on the coil support they prepared earlier. They bend the coil support down to receive the filament, which is made of tungsten. Now they weld one end of the filament to the mount and feed the other end through the little circles of the coil support, then weld it onto the other side of the mount. The mount is now fully assembled. Next, they apply a specific amount of pressure to the bimetal switch to calibrate it. They submerge the finished mount in alcohol to remove any dust or other contaminants. They let it dry for 10 minutes, then apply a liquid called zirconium getter. This draws moisture away from the filament. It's finally time to put the mount in the glass bulb. The sealing machine cuts off excess glass from the bottom, then melts what's left until it attaches to the mount. How will this light bulb work? The electric current travels through the filament to the coil inside the arc tube. The coil warms gases, which then vaporize the small amount of mercury. The mercury vapor then conducts the current from one electrode to another, creating light. The bulbs are made into different shapes and sizes. A machine blows air into the hot glass while a mold creates the form. A special flame lets the glass cool slowly so it won't become brittle from the stress. They print the wattage and voltage on the bulbs, then run them through an oven at 500 degrees Celsius to draw out any humidity or impurities that may be caught inside. Then they go through what's called the tipping torch. It seals in nitrogen gas, which prevents the filament from overheating. Now the bulb is ready for its first test, a 10-minute burn to make sure it operates properly and there's no air inside. Finally, it's time to attach the socket. They apply cement on the base, then hook up the bulb. The bulb passes through a flame that cures the cement. The next machine cleans the socket with acid, so it can be soldered at 2 points. The finished bulbs are put aside for 48 hours, then retested before being shipped out. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net.